Okay, continued to example 3.6. Okay, let's read the question first. A 3 meter high and 5 meter wide wall. So there is a big wall. Okay, basically like this. It's a big, very big wall. Okay, inside that wall consists of 16 cm. So this one is 16 cm. Times 10, 22 cm cross section horizontal bricks with K 0.72 separated by 3 cm thick plaster layer. So 3 cm separated by 3 cm. So from this brick to this brick separated by 3 cm. So like this, we have 1.5 portion here, 1.5 cm portion here. So at the bottom, it's the same. 1.5, 1.5. Okay. There are also 2 cm thick plaster layer on each side of the brick. So each side of the brick we have 2 cm. 2 cm. Okay, and a 3 cm thick rigid form. So this thick rigid form we have 3 cm. On the inner side of the wall, as shown in this figure 3.21. The indoor and the outdoor temperature are 20 degrees Celsius and negative 10 degrees Celsius respectively. And the convection heat transfer coefficient on the inner and the outer side is H1 10, H2 25. Assuming one-dimensional heat transfer and disregarding the radiation, determine the rate of heat transfer through the wall. Okay, so first thing first, calculate the cross-sectional area. Okay, sorry. So if you guys can see here, this wall that consists of brick, plaster and foam is repeatedly, the pattern is repeatedly itself every 25 cm distance, right? Because this from here to here is 25 cm. So every 25 cm we have this pattern of the wall. Okay, so basically the height of this wall is around 25 cm. So in the meter we need to convert, become 0.0. So it will become, 0.25, right? Because need to divide by 100. So 0.25. Okay. So if cross-sectional area, the height we need to times with the width, right? So this width we don't have any information, right? Okay, we actually can assume it. So for easy calculation, we just assume this width is around 1 meter. Okay, just time with 1. Okay, so the area would be 0.25 meter square. Okay, when you already get the area, then basically this question want to know the rate of heat transfer through the wall. So they want us to calculate Q. So Q delta T over R. So delta T we know already, 20 minus with negative 10. And here, okay, before we proceed, we need to firstly draw the thermal resistor network. Okay, we have in here T infinity. So starting with T infinity and then go to R1. Okay, R1 and then we go to Ri first. Ri is a convection part, and then we go to R1, which is this part, and then which is the foam part, conduction. R2, which is the plaster part in here. R3, okay, this R3 we have a combination, we have a parallel layer. So we need to draw the parallel network. So at the top side we have the plaster, so that one we denote as R3. That one is conductance also. So next we have a brick R4. Also the heat transfer is by conduction. Lastly we have a plaster right here, R5. So moving on to the right, we have here plaster R6, and lastly we have at T infinity 2 we have a convection resistant. Okay, so let's calculate one by one like just now. So starting with Ri. So our Ri is here we say that Ri is convection, right? So our convection is equal to 1 over H1A. Okay, so we have H1 is 10, A is 0.25. So the answer would be 0.4 degrees Celsius over watt. So we have next R1. So R1 is a form conduction. So L1 over K1E. So L1 would be, the thickness would be 3 cm, right? So 3 cm convert to meter becomes 0.03 over K1 is 0.72. Sorry, 0.72 is for brick. So for the form is 0.026. Time with area 0.25. Okay, the answer would be 4.62 degrees Celsius over watts. So for R2 conduction also, so basically R2 and R6 is the same. So basically you can use that, you can equal R2 equal to R conduction and also equal to R6. So we have to use the L over KA. So the length is the same, which is 2 cm, 0.02 over K. K for plaster is 0.22 times with 0.25. Okay, so the answer is 0.36 degree Celsius over watts. Okay, now for the parallel part, R3 and R5. So this one, the area is slightly different. So R3 will be equal to R5, right? So it was conduction, heat transfer occur there. Okay, we use L over KE also. So the L is 0. So the L is 0.16 here to here, 116. So the K for the cluster is 0.22, but the area is slightly different because the height is only 1.5 cm. So basically the width is the same, we assume 1 meter. So 1.5 cm we times with 1 meter. Convert first this one to meter and we become 0.015, and the answer would be 48.48 degrees Celsius over watts. Okay, so now we want to calculate R4, the brick side. So the brick area also slightly different. So R4 also R conduction. Okay, over A. So the length, the thickness of that is 16 cm. So 0.16 meter over conductivity 0.72 times with the height of the brick, which is 22 cm. 22 cm, this is area, right? So 22 cm times with 1. So convert first with meter and then you can time with 1. Then we can get 0.22 equal to 1.01 degrees Celsius over watts. So lastly we have RO. So RO is convection. So 1 over H2A. So the answer, so H2A is 1 over 25 times width. So this one we take the actual cross-section area. So 0.16 over what? Okay. So now, as we learned before, this parallel side, the R total is the total of the summation of R3 plus R4 and R5. So we have to calculate, sorry, I use this part to continue my calculation. So R total at the mid, so maybe we can denote as R mid is equal to, so 1 over R mid is equal to 1 over R3 plus 1 over R4 plus 1 over R5. Okay, so just substitute the value that you obtain below and then you will get around 1.03 watt per degree Celsius. So R mid you will get 0.97 degrees Celsius per watt. Okay, so now you need to calculate the overall R total for this whole composite wall. So to calculate the R total, you need to plus Ri, R1, R2, R mid, R6 and RO. So in overall, R total is equal to 6.87 degrees C over watts. Okay, for the Q, so substitute this 20 degrees Celsius minus with negative 10 degrees Celsius over with R total, and then you will get 4.37 watts. Okay. So please remember that you calculate this one is based on area 0.25 meter surface area. So every 0.25 meter square, the rate of heat transfer is 4.37 watt. So if you want to calculate the heat transfer for the total area, which is 3 meter height times with 5 meter wide, okay, first thing you need to calculate the heat transfer per area. So 5.37 you need to over with 0.25 first, and then you will get around 17.5 watt. Okay, this is per 1 meter this is per meter area. The heat transfer is per meter area. So in order you need to know for the whole area 3 meter height times with 5 meter wide, you need to, I continue at the bottom, Q 17.5 times with 15, and then you will get 263 watt. Okay, so this is your first calculation, this is your second, this is your third, and this is your fourth calculation. Okay, so this is the final answer. Okay, move to the heat conduction in cylinders. Okay, consider the long cylinders layer. Okay, we must make an assumption. The two surfaces of the cylindrical layer are maintained at constant temperature T1 and T2. That means all the way this cylinder, inside we have T1, right? Outside we have T2. So all the way the cylinder, the temperature is constant at T1 for the inner part. For the outer part, the temperature constant at T2. Okay, no heat generation, constant thermal conductivity, one-dimensional heat conduction. Fourier's law of heat conduction. So for the cylindrical, it's a bit different with the plane wall just now. So the temperature gradient is along the R direction. Just now varies along X direction. So in here we can see that so the temperature difference is along R direction. So we need to use this 3.35 equation for the Fourier's. Okay, from the Q conduction for cylindrical, from the Fourier's law here, okay, we have to separate the variables and integrate from, for R from R1 to R2, for T from T1 to T2. Okay, so the equation would be like this. Okay, so we need to substitute A equal to 2 pi RL, where the 2 pi RL is a surface area for the cylindrical. Okay, let's integrate together. So here is Q over A Sorry, let me substitute first the 2 pi RL. Q is equal to 2 pi RL. So integrate from R1 to R2. Okay, is negative K, negative K. We integrate from T1 to T2. So after integrate, okay, so this is 1 over R, right? So 1 over R, it will become ln R, right? After integration. So put L here. 2 pi L times ln R. And we have a 2 pi L ln R 2 minus with ln R1, right? Is equal to, if we integrate it, it will become KT, right? So negative K, so T2 minus T1. So we simplify back the equation. Q is equal to 2 pi L. For the ln, we can simplify this equation, right? Ln R2 over ln R1. So is equal to, so we can rearrange back this equation, cancel out the negativity, and K T1 minus T2. So this Q will be equal to, okay, like this, 2 pi L K times T1 minus T2 over with ln R2 over R1. Okay, this is how you can integrate this in this equation from here to here. Okay, since the heat transfer rate is constant, so all this part that in the dotted red line, it will become the thermal resistance for this conduction heat transfer for cylindrical. Okay, thermal resistance with convection. Steady one-dimensional heat transfer through a cylindrical or spherical layer that is exposed to convection on both sides. So the application of this cylindrical layer is a pipeline. Our pipeline, normally inside the pipeline we have a fluid, right? So that fluid can cause the heat transfer by convection, and the outside of the pipe we have also surrounding area. Also the pipe is exposed to the convection. Okay, so we use the same formula, which is Q T infinity 1 minus T infinity 2. T infinity 1 is the temperature inside the cylindrical layer, and T infinity 2 the temperature outside surrounding, over R total, where R total is equal to, for this case, the R total, inside this system we have a convection. So okay, we draw first the thermal resistor network. So T infinity starting here inside. So we have a thermal resistance, our convection inside here. So after that T1, that T1 to T2, we have a conduction heat transfer for, so the thermal resistance will be our cylindrical. So lastly, from T2 to T infinity 2, we have a convection heat transfer. So we need to calculate for our convection. So in here, our convections, we calculate same 1 over HA, but that A is using formula 2 pi RL, surface area. And then for the conduction heat transfer, for the thermal resistance for conduction, we need to use the formula that we derived just now, this one, and convection is the same like before. Okay, so this is the case whereby cylinders have a multi-layered. So steady heat transfer through multi-layered cylinder or spherical shell can be handled just like multi-layered plane. Okay, same goes to multi-layered plane just now, right? We can consider that method to calculate this the heat transfer inside this multi-layered cylinders. Okay, but must be aware that for the conduction heat transfer, to calculate this thermal resistance inside the conduction, we can use the formula that we derived just now. The steady heat transfer rate through a 3-layered composite cylinder of length L with convection on both sides is expressed by equation 3.32, where, so for this one, we can say that inside there is a convection. Starting with convection, this is conduction, 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 and lastly convection. Okay, so convection, we use HA, 1 over HA. For cylindrical, we use the formula that we derived just now. Same goes to here. Or for the conduction, we need to use the formula that we derived just now. So this one is 1 over HA also. Okay. Okay, now I will show example 3.7 on heat transfer to spherical container, and then we will continue with the heat loss through insulated steam pipe. Okay, so a 3 meter internal diameter spherical tank made of 2 cm thick stainless steel is used to store ice water. So inside the spherical tank there is a ice water. The T infinity is 10 degrees Celsius. The tank is located in a room whose temperature is, T infinity is around 22 degrees Celsius. The wall of the room are also at 22 degrees Celsius. The outer surface of the tank is black, and heat transfer between the outer surface of the tank and the surrounding is by natural convection and radiation. So in here we need to consider the radiation, and also mention there is also a natural convection. So this is the simultaneous heat transfer phenomenon. So that means we need to do a parallel network between this natural convection and also radiation. The convection heat transfer coefficient at inner and the outer surface of the tank is H1 is equal to 80, H2 10. Determine the rate of heat transfer to the ice water in the tank and the amount of the ice at 0 degrees Celsius that melts during a 24-hour period. Okay, first thing, find Q. Okay, we need to find area first. So for spherical container, the formula form, so we have two area, which is here A1 and outside area, including this stainless steel. So this outside layer, sorry, the layer that include the stainless steel. Okay, so A1 is inside. Okay, we have pi d square. Okay, pi d square is, so diameter here is 1.5 is radius, so times 2 become 3 meter. So 3 square is equal to 28.3 meter square. So area 2 pi d square over 2. Okay, so the thickness of the stainless steel is 2 cm. So here 2 cm, here also 2 cm. So diameter 3 meter plus width 2 cm plus 2 cm. So it will become 3.04 meter. So the area 2 is 29 meter square. Okay, so like what got mentioned inside here, I'm so sorry, we need to do to draw the thermal network first. Okay, we know that starting from here is T infinity 1. So Ri is convection. So T1 R1 is here, the stainless steel layer. Okay, so the RO is outside here. It occurs simultaneously with a heat of radiation. Then we need to draw like this parallel network, and lastly T infinity 2. Okay, next we have to find the heat transfer coefficient for the radiation. So H rad, taking back the equation that I mentioned inside the slide just now, emissivity, Stephan-Boltzmann, T2 squared plus T infinity 2 squared plus T2 plus T infinity 2. Okay, why we consider this temperature? Because this is the surface temperature that directly contact with heat of radiation, and this is the surrounding whereby the radiation occurred. Okay, but inside this question there is no information on T2, right? If that case, we need to assume T2. Okay, let's say we try to assume T2 is equal to 5 degrees Celsius. So, okay, by assume that the emissivity is equal to 1, because in here got mentioned about the surface of the pipe, right? The tank is black, so we can assume that emissivity equal to 1. So calculate H rad is equal to 5.34 Okay, this one you just put in the Stephan-Boltzmann, and at T2 just key in the 5 degrees Celsius temperature. T infinity 2 is around 22 degrees Celsius, and then you will get this value. Okay, now we calculate one by one Ri until Ro. So for Ri is convection, so 1 over He. Okay, so we already calculate the area here. Just input the value of H1. and you will get 0.0000442 degree C over watt. Okay, for R1, so this one Ri. So R1 is a sphere. So the thickness is the difference between R2 minus R1. Okay. So the area for the spherical container is pi R1 times R2. Okay, here. So R2 minus R1, R2 is 1.5, R1 is 1.5, R1 1.5 meter, R2 we need to plus with 2 cm, which is 1.52 meter. So basically here is 0.02 meter, right? Over with 4 pi time with 1.52, 1.50 K. K is 15. So the answer is 0.000047 degree C per watt. So for RO, we calculate RO first. So RO 1 over, so this one H1, H2, A2, H1, okay. So here we have H2 10 times with 29 meter. The answer would be 0.0345 degree C over watt. So our radiation is equal to 1 over H right times with A2. So 1 over H right just now 5.34 29. The answer would be 0.00646 degree C over watt. Okay, so we need to find the parallel R first. So R parallel is equal to 1 over R parallel is equal to 1 over R right plus 1 over R convection. Okay, so 1 over R parallel is equal to 4.7 watt over 4.7 watt over degree C. So R parallel is equal to 0.002 So R parallel is equal to 0.00225. Okay, degree C over watt. Okay, so our total is equal to, sum up all this one, Ri plus R1 plus with R parallel, and you will get 0.00274 degree C over watt. Okay, so to calculate the Q, okay, 22 degrees Celsius minus with 0, okay, over with this R total, and the Q will get 8029 watts. Okay, also we can also say that the total heat transfer is 80,029 kilojoule per second. Sorry, 8,029 kilojoule per second. Okay, remember just now we assume this H rate. Okay, we need to confirm back whether that H rate that we assume at temperature 5 degrees Celsius is correct or not. We try to put inside the calculation. So we take Q T infinity 2 minus with T2 over R parallel. Just now we have this value, this value, this value, and lastly T2 we will get around 4 degrees Celsius. So close enough, right, to the what we assume. So we don't have to repeat the calculation back. Okay, the second question, they want to know the amount of the ice at 0 degrees Celsius that melt during 24 hours period. Okay, so remember just now this one is kilojoule per second, so you want to know the kilojoule, the heat transfer itself, not the rate of heat transfer. So we have to times 8,029 times with 24 hours is around 24 times with, we need to convert with to seconds, times with 3,600, and then the answer is 693,700 kilojoule. Okay, so that's all for example 3.7. So now we have a look at our last example, which is example 3.8. Okay, steam at T infinity. So T infinity is inside the pipe, is around 320 degrees Celsius. Flow in a cast iron pipe, K is equal to 80, whose inner and outer diameter is D1 5 cm. So inner diameter is the inside pipe here, the grey one. You can see, right, R1, R2 and R3. So for D2 is 5.5 cm respectively. The pipe is covered with 3 cm thick glass wool insulation with K is equal to 0.05. So the insulation part is here, the big one. Heat is lost to the surrounding at T infinity 2, which is 5 degrees Celsius, by natural convection and radiation with a combined heat transfer coefficient of H2. So in here we already given with the information of the combined heat transfer coefficient. So we don't have to do a parallel network. Taking the heat transfer coefficient inside the pipe to be H1 is equal to 60, determine the rate of the heat loss from the steam per unit length of the pipe, and also determine the temperature drop across the pipe shell and the insulation. Okay, so first thing first, let's do the thermal resistor network. So T infinity from the inside of the pipe. So we have the thermal resistance for convection, and then from T1 to T2 we have a thermal resistance for conduction, and from T2 to T3 we have thermal resistance for conduction also. So T1 to T2 is at the blue one, and T2 to T3 at the insulation one, and lastly we have the convection, which is at outer surrounding from the pipe itself. So we calculate A1 first, which is 2 pi RL. So in this question, the value of L is not given. We can assume L equal to 1 meter. So 2 pi, so this is radius 1. Radius 1 is equal to 5 cm divided by 2, convert to meter is around, it is equal to 0.025 meter. So time with 1, and the answer with is 0.157 meter squared for. And then we need to calculate the A3, 2 pi R3, because these two we need to use inside the thermal resistance for convection, right? That's why we need to calculate. So 2 pi, the radius for 3 is, we have 25 cm inside, and then we have to plus with, we have D2 5.5 cm. D2 if we divide it by 2, we will get around 2.75 cm, and then we need to add in the thickness of the insulation, which is 3 cm. So the radius would be 0.0575 times 1, and we will get 0.361 meter squared. So Ri, first Ri convection 1 over H1A1. Okay, I directly give the answer 1.106 degree C over watt. This is Ri. So R1, we have a conduction, right? So conduction for cylindrical, remember we need to use this formula that we derived before, ln R2 over R1 over with 2 pi K1L. So we have R2, we have R1, we have K1, L we assume 1, and then the answer would be 0.0002 degrees Celsius over watt. So next we have R2. So R2 is the same with the R1. That means we need to use the same formula, not the same value. R3 over R2. So 2 pi K 2 L. So for R2 is the insulation pipe. So the thickness that we need to use is R3, and difference between R3 and R2. Okay, the answer would be 2.3 degree C over watt. So lastly, RO 1 over H2A3. So H2, given the combined heat transfer coefficient 18, A3, use this value and you will get 0.145 degree C over watt. Okay, so R total, so this one is a series network, so just total up all everything and you will get 2.61 degree C over watt. Okay, to find the Q, you need to find the difference between T infinity 1 minus, T infinity 1 minus T infinity 2 over R total. So we already know the T infinity 1, which is 320 degrees Celsius, T infinity 2, 5 degrees Celsius. Okay, the answer would be, so here 25 over 1 to 1 watts. Why we we have to find the differentiation, why we have to find the difference between T infinity 1 to T infinity 2? Because the heat loss from the steam. So the heat transfer will be occurred from the hot medium to cold medium, right? So we take this as a T infinity 1, T infinity 2. Okay. And also determine the temperature drop across the pipe shell under insulation. Okay, to find the temperature drop for the pipe, okay, delta T pipe. So we use the formula Q equal to delta T over R. So for this one, for pipe, so R that we need to use is R1. So delta T here is 0.02 degrees Celsius. So the other one is the insulation, delta T insulation. So Q times R2, right, for the insulation. So the answer would be 284 degrees Celsius. Okay. So I think that's all from example 3.8. So I hope you can try each one of the example that I show you inside this video. Okay, thank you.